Hello, welcome back. Now that you know how to solve a right triangle, find all the missing information about angles and sides using Pythagorean theorem or your sine, cosine, or tangent ratios, we're going to look at some application problems. So we're going to look at basically word problems that are going to use those skills. So applications for solving right triangles. So I'm going to go through a whole mix of applications that you might see and do an example of each kind. Okay. First example is actually going to deal with something called angle of elevation. The problem says that the angle of elevation from a point on the ground from a point on the ground that's 15.5 meters from the base of the tree to the top of the tree is 60.4 degrees. Find the height of the tree. Angle of elevation from the ground to the top of a tree is 60.4 degrees. Then the distance from the base of the tree is 15.5 meters. So you can say maybe you're standing 15.5 meters from the base of the tree. And we want to find the height of the tree. Okay. And after I get done writing down the problem, it's going to be very important to draw ourselves a picture. With all of these problems, it's very important to draw a diagram. That way you can really see what's happening, really visualize what's happening, and make sure you get everything labeled and so forth. Okay, so we've got this tree. Somebody's standing over here, and we're told that that distance on the ground there is 15.5 meters. And the angle of elevation is the angle made looking up from that point to the top of the tree. So that angle right there is 60.4 degrees. That's what they mean by angle of elevation. It's like basically if you're looking up or if you're going up, like if an airplane's taking off, the angle of elevation is the angle it makes with the ground. If you're looking up at the top of the tree or the top of a building, that angle that is made with the ground here is the angle of elevation. And the question is, what is the height of the tree? Okay, so we know the angle. We're trying to find the opposite side here because basically we've got a right angle here. Even though my sketch isn't drawn very well, we've got right angles. We've basically got a right triangle going on here. We know we're trying to find the opposite side. We know the adjacent side. Well, in trig, we know that tangent of theta can be found by doing the opposite over adjacent. So in this case, the tangent of 60.4 degrees is going to equal opposite, which we're trying to find, over adjacent, which we know. Multiply both sides by that 15.5 meters, and you can solve for x. So 15.5 times the tangent of 60.4 degrees. Okay, so let's get trusty calculator out here. Do 15.5 times the tangent of 60.4 and see what that gives us. And since we had 3 significant digits in our numbers in the problem, we'll just round to 10th place and give us 3 significant digits here. So about 27.3. So x is about 27.3 meters. So that tells us about how tall the tree is. It's about 27.3 meters tall. Okay, so that's an example with angle elevation, and we ended up using tangent there. Okay, next, let's do angle of depression. Find the angle of depression from the top of a 97-foot building to the base of a building across the street located 42 feet away. Alright, we've got 2 buildings here. We're not worried about how tall the buildings are, really, at this moment. This one we know is 97 feet according to the problem. So this building here, we're looking at 97 feet. Then we're told that the angle of we're trying to find the angle of depression from the top of the building to the base of the other building. Okay, so if you're standing up here, angle of depression would be this angle. Like if you were looking straight across, you'd have this line. Angle of depression is the angle made when you're looking down to another point. And we were told that the other building is 42 feet away. Okay. So if you want to, you can look at this as, right here we got this right triangle. We know that this has to be 42 feet. And we know that this has to be 97 feet. And we're trying to find this angle. You can go ahead and call it theta if we want. Well, we've got from theta, we know the opposite side, we know the adjacent side. So we know tangent of theta equals opposite over adjacent. So if we want to find theta, we can do the inverse tangent of 97 over 42 and see what that gets us. Okay, so second tan for the inverse tan, 97 divided by 42. Hit enter. And let's see, our numbers all had like 2 significant digits, so let's go and round to the nearest whole degree and get 67 degrees. So that's that angle of depression, 67 degrees right there. Okay, next we're going to talk about bearing. Bearing is a concept in navigation, like what's your location, what's your bearing. If a single angle is given, that's understood that the bearing is measured in a clockwise direction from due north. So knowing that, that'll help us with bearing problems where just they give you a single angle and that's it. Clockwise from due north. Okay. So let's say they tell us there's 2 radar stations, A and B, that run on an east-west line. We have radar station A here, and then radar station B here. They tell us it runs on an east-west line, so like the horizon there. And then they're 8.6 kilometers apart. Station A detects a plane at sea on a bearing of 53 degrees. Okay, so a bearing of 53 degrees means like this would be due north from station A. A bearing of 53 degrees means you're going this direction here, clockwise, for 53 degrees. Okay, then the airplane from station B simultaneously detects the same airplane on a bearing of 323 degrees. Okay, if you're talking about due north this direction, 323 degrees is going to take you clockwise around. And that's how you're going to get 323 degrees. Now if this is, you have to go clockwise from due north. And if that's 323 degrees, let's see, 90, 180, 270. Let's figure out what this little amount here is. 323 minus 270 is going to give us 53. So this little amount right here is 53 degrees. And for the other one, if this is 53, going all the way would be 90. So if you do 90 minus 53, you'll get that this right here is 37 degrees. Now, we might need that. Let me finish. Okay, I got distracted. All right, so what are they asking us? They're saying find the distance from B to C. So they're saying find this distance right here between B and C. Well, what do we know? We know, if we know this one's 37 and that one's 53, that adds up to 90, which means that this must be 90 right here. If these two add up to 90, then this one has to be 90 because triangle has to add up to 180. So we've got ourselves a right triangle. And we're trying to find this length. So we can do this any number of ways. I'm looking at this. If I know this is 53 degrees, adjacent over hypotenuse would be my cosine of 53. So you can use that. It's not the only one that's possible, but this will work. So you can solve for x, multiply both sides by 8.6, and see what you get. Got two significant digits here, two there. So I'll make sure I have like two places. So, oops, covered it up, sorry. Let me minimize that. Alright, I'm taking 8.6 times cosine of 53. I had to go back and see exactly what I was doing. 8.6 times cosine of 53. Enter. I get 5.175. So I can say round it to tenths place, 5.2. So I can say it's about 5.2 kilometers. Okay. So that's an example with bearing. Now that's not the only kind of bearing problems. You can also have bearing that starts with a north-south line and using an acute angle to show the direction either east or west from this line. In other words, you can also have bearing readings like that start out either north or south and then so many degrees east or west. Like if you have a bearing that says north 18 degrees east, what that means is you've got due north going this way, and then you're looking at the bearing is 18 degrees off of that in the easterly direction, because east is that direction. If it says north 18 degrees west, then you've got your north right here, and then that's 18 degrees off of north in the westerly direction. If you have south 18 degrees west, then you're going south, and that's 18 degrees off to the westerly direction from there, or if you have south 18 degrees east, you're heading south, and then you're heading southeast, basically 18 degrees off of south. So that's other ways that bearing can be talked about. So let's say, another example, let's say we have a ship that leaves port and sails on a bearing of south 34 degrees west for 2.5 hours. Then it turns and sails on a bearing of north 56 degrees west for 3.0 hours. If the ship's rate of speed is 18 knots, nautical miles per hour, find the distance that the ship is from port. Okay, so for this one, let's see here. We've got port. It's so important to draw pictures and tell us what's going on. Sails on a bearing of south 34 degrees west. So it's sailing in this direction basically, because south is here and it's 34 degrees off of south in the westerly direction. And it does that for 2.5 hours. So if it's going 18 knots, that's nautical miles per hour. That's 18 nautical miles per hour. And it's doing that for 2.5 hours. You can multiply 18 times 2.5. to see just how far it goes, how many nautical miles it went. 45 nautical miles. Okay, and then it ended up here. Then it turned. And it says it turned and sailed north 56 degrees west for 3 hours. So we're looking at, if you're looking at north 56 degrees west, it's going in this direction. Because north would go like this, and then it's 56 degrees off of that right here. So let's look at that for a second here. Speed 18 knots. So again, 3 hours times 18 knots, we're looking at 54 nautical miles there. And then the question's asking, how far from port is it once it gets to here? So it starts here, goes to here, turns, and goes to here. And once it's here, how far from port is it? Alright, so basically we've got a triangle here, but we've got to think for a second about what this triangle means. What are the values? Let's see here. If this angle here is 34 degrees, I'm going to reason out just how many angles I've got going on here. If this angle is 34 degrees, that means this angle here must be 56 degrees, which then means that this angle here must be 34 degrees. Because, and if you think about it, actually it's like two parallel lines. Got a parallel line here and here, You got this transversal. You have opposite interior angles. These two are going to be congruent, 34 and 34. But I was also, when I was first thinking about this, I was thinking about it in terms of making a right triangle. If you've got due south, then go across there and make that a 90-degree angle. We knew that this was 34. These two have to add up to 90 to make the right triangle. So this has to be 56. Then if you want to make this a right angle, if you have 56 here, that has to be 34. Okay, so this right triangle, let me re-sketch it. It feels messy. Let me re-sketch it. It feels really messy right now. We've got a 56-degree angle and a 34-degree angle together make 90 degrees. So I know I'm dealing with a right triangle. I know that this here was 45 nautical miles and this here was 54 nautical miles. And I'm trying to find this. I can use Pythagorean theorem. 54 squared, the two legs squared, added up, has to equal the hypotenuse squared. Let's try to do a question mark. Alright, so let's use the calculator, see what this gives us. See if we do 54 squared. Why did it do that? 54 squared plus 45 squared, and then do the square root of that and see what we get. Okay. Now since our numbers had two significant digits, let's just round this to 2, so 70. So we could go ahead and say 70 nautical miles from port. So there we go. So that's an example with bearing. Alright, 2 more examples. This next one is going to use trig to measure a distance. There's something called the subtense bar method. It's a method that surveyors use to determine a small distance d between 2 points P and Q. The subtense bar with length b is centered at Q and situated perpendicular to the line of sight between P and Q. Okay, let me draw a picture. We have point P and we have point Q. Okay, surveyors are trying to measure distance d between these 2 points. Okay. Then the subtense bar length, they use b. So we have subtense bar over here, whose length is b. But this half will be b over 2. This half will be b over 2. But we made a little triangle here using triangles. Alright, forgive my sketching, it's bad. And then you got angle that's made right here is theta. Okay. And the subtense bar is situated perpendicularly, which means like this line of sight between P and Q, the subtense bar is perpendicular to that. It makes a 90-degree angle with it. Alright, so we've got this 2 right triangles here basically. Okay. Now let's say we know that theta is 2 degrees, 41 minutes, 38 seconds. And let's say we know that b, the subtense bar length, is 3.5000 centimeters. So those 3 zeros there are significant. Somebody measured and said, well, we can say it's accurate to that many decimal places. So there's actually like 5 significant digits there. Alright. So let's try to find d. Find that distance, knowing this information. Well, if we look at half of that triangle, we've got a right triangle going on there. we're trying to find D. We know theta is 2 degrees, 41 minutes, 38 seconds. So this right here is half of, this angle here is half of 2 degrees, 41 minutes, 38 seconds. And then if the subtens bar is 3.5000 centimeters, then this is half of that, which would be 1.7500 centimeters. Okay, so from there, we've got enough information to help us to find D. Let's see. Tangent is opposite over adjacent. So the tangent of that 1/2 of 2 degrees, 41 minutes, 38 seconds is equal to 1.7500 divided by D. We'll multiply both sides by D. You're going to get 1 point, and then divide both sides by tangent, and you get this. So we can use that, put it in our calculator, and see what we get. We've got 1.7500 divided by the tangent of 0.5 times 2 degrees. Might as well use the calculator numbers, calculator symbols. 41 minutes and 38 seconds. Oops. Sorry, trying to see seconds here. My eyes are not focusing very well. All right. So hit enter, and there we go. Let's see, this 1.7500 was to 5 significant digits. Let's take this to 5 significant digits. So 74.427. So 74.427. And that distance measurement was in centimeters. So apparently D is 74.427 centimeters. I was trying to circle that and it didn't go through. But that's how you could be a surveyor and figure out that distance. Okay. Then one more example. This one involves solving a problem involving angles of elevation again. We're going to revisit angles of elevation. But it's a situation where you really can't truly know how far from the base of something you are. Let's say you have a mountain, and you're standing over here, and you're trying to spot, you know like what the angle of elevation is from where you are to the top of the mountain. But you have no way of knowing what this distance is, because you don't know how deep into the mountain you'd have to go to get to the halfway point, to get like right underneath that peak. And you're trying to find the height of the mountain. How do you do that? Actually, there were some people who had to do this with Mount Everest. In the 1930s, a National Geographic team headed by Brad Washburn used trig to create a map of the 5,000 square mile region, Yukon. They used a bunch of angles and so forth, but also trying to do the top of Mount Everest. They couldn't really see how far they were, the expedition, So they had to use trig, and they had to use angles of you could measure angles of elevation using certain instruments. They had to be a little bit creative with trying to figure out how to get the height of the mountain. Because I mean, even if you climb to the top of Mount Everest, you really don't know how far down or how far above the ground you are when you're at the very top. And you can't really mine or drill into the mountain and try to measure it. So this has been something that's been used for mapping out all kinds of territories, all kinds of regions. But basically, the way it works is going to come up in this next example. How do we work it? All right, this next example. Let's say you need to find the height of something. So you're trying to find the height of something right here. And let's say at one point you know that the angle of elevation to the top of it is 74.2 degrees. Get this thing to walk. Then you can walk a little bit further. Let's say you walk 35 feet further. And from there, the angle of elevation is 51.8 degrees. How do you find the height of the building when you don't know this distance here? You don't know how far away you were from the building here. You still don't know how far away from the building you are here. You just know that you're 35 feet further than you were before. Or from the object, mountain, building, whatever. Because maybe you have no way of truly measuring this distance. How do we find the height? Well, we've basically got two right triangles going on here. We've got this right triangle here, where the tangent of the angle, 74.2 degrees, equals opposite side x over adjacent side y. But then we've got a bigger right triangle where the tangent of the 51.8 degrees equals opposite side x over adjacent side 35 plus y. Well, in the first equation, you can solve for x. X equals y times tangent of 74.2 degrees. Second equation, solve for x. X equals 35 plus y times the tangent of 51.8 degrees. In both situations, x is the same measure. So you can set y tan of 74.2 degrees equal to 35 plus y tan of 51.8 degrees. And this is how the Mount Everest expedition measured the height of Everest. They weren't these numbers exactly, but it was this process, this kind of trig process. Try and drag that down a little bit. Alright, so distribute 35 over here. You got 35 times the tan of 51.8 degrees plus y times the tan of 51.8 degrees. Subtract from both sides. You got y tan of 74.2 degrees minus y tan of 51.8 degrees equals 35 tan of 51.8 degrees. Factor out y. You'll have tan of 74.2 minus tan of 51.8. Then you can divide both sides by that. Then put all this in our trusty calculator and see what it gives us. I like to put it all in at once so I don't have to worry about rounding or anything. Alright, so on the top I can put tan of 51.8 degrees And then on the bottom, I'm going to put the bottom in parentheses, so just to make sure everything works out. Tan of, whoops, tan of 74.2 degrees minus tan of 51.8. Then close parentheses, closing the denominator, and hit enter. Let's see here. Something doesn't look quite right, so I must have typed in something not quite right. I had tan of 51.8. Oh, I didn't see it. 35 times that. Ooh, okay. Let's see here. Yeah. All right. Let me try this again. Sorry. That's what I get for having this taking up too much of the screen. See if I can make this a little smaller so I can see what I'm doing here. All right, that's kind of better, but it might not work very well. All right, let's try this again. All right, in the numerator, I got 35 times tan of 51.8. Then divided by the denominator, I got tan of 74.2 minus tan of 51.8. Hit enter. Okay. So that gives me y. Now I know how far away from the building started at. So around 19.7, whatever the units were. I think it was feet. So now I know what this measurement is. If I wanted to know the height of the building, or object, that's x. Well, x is the same thing as y times tan of 74.2. So I can go back and find that as well. There's all kinds of ways to do this, but so I can take that number times the tan of 74.2, and that'll give me my x. So around 69 feet. So whatever this object is, it's around 69 feet tall. So this object wasn't a mountain. In fact, it was supposed to be a building. But that's the same way. If it was a mountain, you can do the same thing. As long as you know your angle of elevation at one point, you can back up, measure how far you backed up, and see what your angle of elevation is at that point. Yeah, the thing with the Mount Everest measurement, it's pretty amazing. The surveyors, when they used this trig, they obtained a height of around 29,000 feet to the nearest foot. But they thought no one would believe that measurement of 29,000 feet, so they reported it as 29,002 feet. But it's pretty close to the real measurement. They were just using basic trig and were able to find that. And it turns out that Mount Everest is actually around 29,029 feet. So they were only off by maybe 27 feet. Pretty remarkable. Just using these kinds of measurements. Alright, well, I hope these applications are enough to kind of pique your interest. Thank you for joining us, and next time we'll be diving into some more triangles. That's the name of the game with trigonometry. Looking forward to seeing you again.